Okay, thanks for the organizer for the invitation, and also I hope you all had a nice time in Beijing. So today I'm going to project. The goal is to compute the subleading order corrections for the current three-point correlators in the large expansion. So here's the outline of this talk. So first, I will explain the background of the current three-point correlators in safety. So it has been known for decades. And then I will explain the motivations that why do we care about the current three-point correlators. And in the second part, I will explain I will use the own vector model as an example to show this the method, how we can compute the sublinear order corrections for the current three-point correlators systematically. And the key point of this method is the method of subgraphs for the loop integrals in safeties. So I will explain what's the technical details about this new method. And in next part, I will show how this method can be used to compute the some of the current three-point correlators that have very interesting applications in condensed matter physics to compute the conductivity and so on. So first part, the background. So in 1993, Osborn and his student, Pedicles, they studied the restrictions of the conformal symmetry and the conformal two-point correlator and the three-point correlator systematically. And they found that because of conformal symmetry, the conformal two-point correlator and also three-point correlators can be almost fixed up to few free parameters. And also because of conformal mode identities, the free parameters in the current three-point correlators can be further reduced. This is a brief summary of this the result just obtained by Osborn and Pedicles. So for the conserved current J three-point correlators are only two free parameters in general dimensions, and these functions that provide can be realized by free boson and also free fermions. And similarly for the TJJ and the TDTT. So here in this talk, we will only focus on the party event sectors and also there are some subtleties about the three-point correlator of stress tensor, right? In different dimensions, there will be slightly different parameters. So here, that's the background of what are the current three-point correlators. Then the question is that why do we care about the current three-point correlators? So here are a bunch of reasons. I will go through these applications briefly. So the first part, so the current three-point correlators, they have very fundamental applications in condensed matter physics. For example, so as we know at the quantum critical point, it is described by a safety. And the current operator J has OP, JJ, given by this bunch of operators. And then the conductivity near the quantum critical point at finite temperature, because we know the quantum critical point usually happens at the Z temperature. Well, usually at finite temperature, then the conductivity, which is given by sigma, can be approximately expanded by this series. That determined by the first one is the YCAM operator or unit operator in safety. The second one is contribution from the leading signet Skinner operator in the series. And the third one is the contribution from stress tensor operator. While in some safeties, if the signet Skinner is irrelevant, then the second term will be not important, or it won't appear here as well. So the leading order, so as you can see that here, to compute the quantum critical point, it's very important to know the current three-point correlators lambda JJS and also lambda JJT. So the leading order result for lambda JJG and also TJGG has been computed by Martasina, Subia and other people about more than 10 years ago. Well, it's hard to compute the OP coefficients to the high loop corrections. So usually people use Monte Carlo simulation to study the conductivity. So that's one of the motivations that the current three-point correlators have very fundamental applications in condensed matter physics. And another application is in conformal bootstrap. So this is a new result from David Simondolf and David Portland's group appeared in last November. What they did in this new plot is that they introduced a stress tensor in the bootstrap setup, and then that means they explored the constraint from the current correlators in the bootstrap constraints. And they found that because of the constraint from the stress tensor current correlators, the bootstrap precision can be improved significantly. So the lesson we learned from this work is that in bootstrap setup, the constraint from conserved current operators are very helpful. So this is an example that we studied that use bootstrap to study the strongly coupled gauge theory. That's a typical example of the four-fold gauge theory, and with some assumptions which are posed from Zhijin expansion result, we can get island. This island, of course, is not as small. So our hope is that by introduce the current operators in the bootstrap setup, we can get much more precise result for the liquidity 3. But here to introduce or to explore the constraints from the conserved currents, then it's very important to have some idea or to know some information about the current superpoint correlators. So this is another very important motivation for us to study the current superpoint correlator. And another application for the current superpoint correlator also appears in the so-called conformal collide bands. There's a lateral question. Since Osborne, Dorn, and Petkus, people realize that for the current superpoint correlators, the superpoint functions are almost fixed up to few free parameters. Well, before this group, people usually believe that, okay, they didn't realize that for these free parameters, they have some strength constraints about the possible values of these parameters. But Martesella and Hoffman, the first proposed that for these free parameters in the conserved current superpoint correlators, actually you cannot choose the values of these parameters as big as you want or as small as you want. Actually, they are restricted by the constraint from the causality and positive so on. And now, later, this constraint also generalized by Myers and also Subasakdev and other people to general dimensions and for different conserved current correlators. So this is a list of the restrictions proposed by these people and the parameters of the current superpoint correlators. So this is called the conformal collide band, and it has been proved using an bootstrap based on the coarsen symmetry of the 4-point functions and the unitarity, and also the pick up the spatial net limit. Then they provide a strict proof about this parameter space, the range of the parameter space. So this conformal collide bands has very important applications in QCD and also holograph and so on. So another interesting application of the current superpoint correlators proposed by Madison and his student at that time. So they propose that for the during inflation, we know that the leading order approximation of this of the universe is given by the de Sitter space, and they ask this question: during inflation, it's possible to generate the non-Gaussian entities. Well, and one of the interesting non-Gaussian entities is the gravity non-Gaussian entities. So it corresponds to the gravity and superpoint function GGG in the de Sitter space, and they studied that due to the de Sitter, the superpoint function, the GGG superpoint function can have two-party even shapes. Well, we know that in high energy, it's possible that we could have very different or various kinds of higher derivative corrections to the gravity theory. During inflation, that's we know that in any stage there's a slow inflation process, right? We don't know. They just studied the restrictions and superpoint correlate from the isometry. So if the isometry of the de Sitter space, they do not employ a specific safety due to this theory. And as you may know, right, the safety due to de Sitter space is kind of very subtle. I don't think people have a very concrete example about this during it. Yeah, exactly. It's just kinematics. Related to what, sorry? Well, in this book, they didn't propose so much. They just introduced the restrictions from the isometry, de Sitter isometry, and this is a leading order approximation of the inflation process. So there's no concrete de Sitter safety correspondence here. But here, it's kind of evidence, so don't take it too seriously. And so from the isometry constraint, the people realize that Madison and his students realize that there can only two independent coefficients TGT in 3D safety. In the gravity non-Gaussian entities, actually, this is not a strict correspondence, but it corresponds. It's kind of like the independent coefficients of TGT in 3D safety. There are only two independent tensor structures. But there's another question that for the gravity non-Gaussian entity, we know even for the non-Gaussian entity from the cosmological observations, we know it's extremely small, and if it's non-zero. And there's a natural question that just theoretical question: how big, how strong the non-Gaussian entity could be? So this leads to another question, another interesting proposal. Like the first proposal is that so from a constraint from causality and some other properties, and people proposed that they so-called the CEMZ, one of the authors in the audience, and for the Einstein graph, A equal to A charge equal to C charge, and if we introduce high derivative corrections in A and C, there will be some small difference, but the difference is restricted by this constraint. Well, this is another interesting proposal called Swapland conjecture. They propose that for the in the ADS, if it's non-supersymmetric theory in the ADS, then the theory cannot be Einstein-like. So, or if in ADS, if it's Einstein-like gravity, then it has to be supersymmetric. This is a conjecture again; it's not strictly proved. Well, if we combine these two statements together, then it seems that there's a statement that for the non-supersymmetric, you cannot have large gap in a single spectrum, a single trace spectrum. So this is an example for the to show the potence of the current superpolar correlators in the holographic and quantum gravity series. Well, the goal of this work is that to develop a systematic approach to compute the higher order corrections of signature charge and some other parameters for the current superpolar correlators. Using, of course, we will start from Lagrangian and then use Lagrangian method. So we will take the own vector model as an example to show this method. So for the own vector model, so usually we start from the UV fixed point safety zero, and then we introduce the double trace deformation. Then the theory will, this deformation will generate arch flow, and then it's likely that it will go to another fixed point in the IR. And we use unit Hubbard transformations, and we can get that this auxiliary scalar field will obtain a propagator. So at the IR fixed point, the Lagrangian or the action of the theory can be is given by this this formula. So here we have our own vector scalar phi I, and also we have a critical scalar sigma, and these are the effective propagators of the theory at the IR fixed point. So then we use the usual renormalization scheme, which induce the renormalization parameters and so on. These parameters can be fixed by the band loop diagrams and so on. So this is the usual approach, but actually, technically, it's not easy to realize to do the computation. Here's one example. For the QED3, if we want to compute the large subleading order corrections of the TJJ superpolar correlator, we have this Feynman diagram. So for example, for these two, actually they are the three extender, they have three legs and also the loops. So it's not easy to compute these Feynman loop diagrams. This is one of the challenges to compute large expansion of the current superpolar correlators. Sorry, say it again. And here, of course, you have moment conservation one, and then you already have two independent external momentum. But the general formula, so your question was that the momentum dependence was fixed by conformal symmetry? Yeah, in principle, that's true. But technically, it's not ever go to that point later. Yeah, you're right, actually. So, so this is one technical point that if we really want to compute the current superpolar correlator boundary corrections, then we need to compute three external leg and also three loop Feynman diagrams. And it's not easy technically. Of course, as he just mentioned that because we are working on conformal symmetry, conformal field series, therefore, so we can use the conformal symmetry to simplify the problem. One thing is that the conformal symmetry fix the current superpolar correlators up to free parameters in position space. Then you may expect that if you just need to take a Fourier transformation, then you go to the momentum space, and then you get the dependence of the moment of the Feynman diagrams and the momentum. So that's true, but it's technically it's not easy. You will see a reason why. So for example, for the stress tensor and also other operators, we can realize this superpolar function from free theory or free Feynman theory, and then you can get the general functions of the Feynman diagrams in momentum space, and you fix the free parameters from Feynman diagrams. But the challenge, another challenge is that in momentum space. form of three-point function are remarkably complicated in momentum space. This is first studied by these people. So they were motivated by Mardesa's work. They were working on cosmology, early time cosmology. And motivated by Mardesa's work, and then these guys, they want to study the like the stress tensor three-point collider in safety side, and they want to get some lesson from the safety side to the any stage cosmology. That's their motivation, but they found it's not easy. This one concrete. Also, another team. This is another team from the condensed side should be effective. They also need to know the information about three-point collators to study the like the conductivity near the quantum critical point, and they tried to compute the three-point collator of GGGG and also GGGG, but they can only get the leading order result. So but actually even for the leading order result, for example, assume this is a general three-point collator in momentum space. So one motivation is that you just take Fourier transformation of the three-point collator in position space, and you get it in momentum space. But this is the general expression of the three-point function in momentum space. Actually, it is given by an integral of the three modified Bessel functions of second kind. Well, you can imagine it's hard to get an analytical expression for this integral result. So that's a challenge. Of course, we are the physicists, right? Every time when we have such kind of complicated mathematical problem, we can always try to take some serious expansion to solve the problem. But the problem is how to expand the conformal integrals, for example, for the three-point function momentum space. Namely, we may take that we can just take up one of the external momentum like P1, assuming it is much smaller than P2, then we can take the tiny expand of the integrand in this limit. But this is a subtle problem. The problem is that when we take this limit, take this tiny expansion of the three-point collator, in this limit, we always need to play with the internal momentum K, which we integral over. And then the integral region is actually the whole range of the momentum space. Good point. Yeah, good point. So in 3D it's a little bit special, and we will also get to that point later. Yeah, thanks for the question. But in general now, in general space-time dimension, then there's the conformal integral, and then you have this problem that when you take this limit, then you always need to play with this subtle issue that the integral internal momentum, actually they integral over the whole range. So in some regions, they could be smaller than this small parameter. And then you need to, so if you namely take some Taylor expansion of the integrand, then you will get the wrong result. So actually there could be two methods to solve this problem. One is the so-called expansion by regions. So the idea is that because this certain problem comes from the special region of the internal momentum, which is smaller than the small momentum or larger than the large momentum. So we just divide or separate the integral regions into different pieces. So in one piece, we can, in different regions, we can take the tangent expansion with respect to different variables, which are to be small compared with other momentum. So this expansion by regions has been widely applied for the people in the QCD or some other directions. So they found that it can always give you the right answer, but it's not strictly proved yet. And it's still under development. So people try to find the different method to discover the different regions and how to take the tangent expansion in different regions. And there's another method for the expansion by subgraphs. The point is that assume you have a very complicated Feynman diagram with high loops. And then when you take the Taylor expansions, you just separate the whole subgraph into different pieces. And so for this expansion by regions, actually people can prove that this is strict in Euclidean space. So we will adopt this. The good thing is that for our computations, we are in Euclidean space, and this method is strict. So that'll be very helpful for us to compute the sublinear order questions. So what is the method of subgraph? Let me give you one simple example. Let's consider this three-point collator, phi square. Here, phi is the free scalar in general dimension. Then this three-point collator is given by this one loop diagram. And if we, again, as I mentioned before, even for this one loop diagram, if you want to compute this integral, you will get an integral over product of three second Bessel functions. And it's hard to get an analytical result. But use the method of subgraph. So the idea is that here, let's assume that P1 is small and P2 are big compared with P1. Now we want to take a tangent expansion of this Freeman diagram. So actually, the idea is that we just pick up two external points, contains the largest momentum P2. That means this point and also this point. Then we just pick up all the possible paths connecting these 2 points. So, and for different paths give you different subgraph. So of course, the most simple one is the original Freeman diagram. That's the one loop diagram. That's the first subgraph. That's the Freeman diagram itself. And also we can pick up another line, which connects these 2 points directly. That's another subgraph. But you may wonder, can we pick up these two lines? But actually, they give you it will give you the result because this is a conformal integrals. It's massless integrals. So finally, we can just get these 2 parts for the Freeman integral for this one loop integral in the expansion. So the interesting point is that for the first subgraph, it has a singularity for general D for the momentum P2. But for the second subgraph, it has a singularity for the momentum P1. So that means for these 2 different pieces, we have 2 different singularity behaviors. That's very helpful for us to trace the contributions from different subgraphs. And similarly for the GGG, we can do the same thing, and we compute. Even though it's hard to get an analytical result for this one loop integral, but using a set of subgraphs, it's easy to get the contributions from different graphs. And if you can expand this expansion to arbitrary high order, and you can get the result as precise as you want. While in like in QCD computations, people go to like the 8th order or even 10th order to get a precise result. But for safety, the funny thing is that you only need to go to the sub-leading orders, and that's enough because it's conformal symmetry. We only need to fix parameters. Now let's go to the we want to verify this result. So this is 3D, which you mentioned that. In 3D, things are a little bit different because in 3D, if you count the powers, it's conformal integral. Of course, here we have tensor structures, but you can show that they can be reduced to the conformal integrals after you take the tensor reduction. And then, because it's conformal integrals, so we can get an analytical result for these integrals. And then this is the analytical expression for the conformal 3-point correlator of JJJ. Here we have the complicated tensor structures which were iterated. The higher order terms. And then for the previous result, it works in general dimensions. So we can just take a d equal to 2 and then compare this exact result. We find the match result with each other exactly. Again, it's an interesting point is that we have 2 different pieces or from 2 different subgraphs. They correspond to different singularities for different momentum. That's very important for our next computations. And similarly for the TJJ, we can do the same thing. We can take the subgraph expansions, and even though originally the integral is complicated in general dimensions, but after we take a subgraph expansion, we can people can evaluate the integral very easily. And for the key point here is that in general for the 3-point correlator, even no matter for the current or scalar, we can after we take the method of subgraph expansion, we can always separate the whole integral into 2 pieces. One is singular with respect to P2 momentum, another one is singular with respect to P1 momentum. So this is just one loop integral, so it seems to be quite trivial. So let's consider the 3-loop integral, which appears in our one loop in our sub-leading order corrections in the larger expansion. So for example, here this is a TJJ's 3-point correlator. We have 3 loops. This dot corresponds to the propagator of the critical boson. And for the solid line, corresponds to the propagator of the Owen vector scalar. So for this 3-point and 3-loop integral, if you want to get the analytical result, it's quite difficult. But here we can use the subgraph expansion. Again, the idea of the subgraph is that you pick up 2 external point contains large external momentum. That means there's J0 and J sigma. And they find all the paths connect these 2 points. So the first one is the 3-loop graph itself. So in this case, we will just count the for the momentum, internal momentum in the subgraph, they consider as big or as large momentum. We cannot take a Taylor expansion for this internal momentum. But for all the other momentums or external momentums outside of this subgraph, they consider to be small. And we take a Taylor expansion of this external momentums and also this internal momentum that outside of this subgraph. So for the first subgraph, that's the three-loop Feynman diagram itself. Then in this case, we have three internal momentums. They are considered to be big, so we cannot take tangent expansion for these internal momentums. So we just take the tangent expansion for the small momentum P1. Well, another subgraph is this given by this two-loop diagram marked by these red lines. So here we have the one external momentum P1 is small, and another one is the internal momentum for the first loop. It's also small because it is outside of this subgraph. So here in the second subgraph, we have two small parameters, P1 and K1, and then we just take a tangent series expansion for the integrand of this subgraph. And similarly, we have another two subgraphs given by with different small momentums. So our goal is that we want to use this method of subgraphs to compute the super correlators of JJ and also TJJ. And so just by using the method of subgraphs, the good thing is that, for example, for the three-leg integrals, the insertion rate can reduce to two-loop, two-leg integrals or even simpler ones. That means that helps us a lot so that we can do the computation analytically. So here's one example for the JJ super correlator. Here's the Feynman diagrams for this JJ super correlator given by these four diagrams. And we use the method of subgraph. Above the integrals can be expanded into two parts, as I mentioned before. And actually, we can do the evaluate the Feynman subgraphs directly, and they're given by this result. Again, for the two pieces, I uppercase gamma and I lowercase gamma, they have different singularities in P1 and P2. So, for example, for the I uppercase gamma, the Feynman integrals of the four Feynman diagrams are given by this one. After combining them together, they lead to the subleading all the corrections to the lambda JJJ, which is given by this formula. And also, similarly, we can use the same method to compute subleading all the corrections for the lambda JJJ in coarse living model. We can get a similar result. And of course, we can apply a similar method for the TJJ and the TJT, but then you need to go to higher loops and also play with the more complicated structures. But the method are the same. So then let's go to one interesting implication of this method here. As I mentioned before, in condensed matter physics, there's a very interesting point that usually we have the quantum critical point at the temperature and you tune the coupling G. But usually for the real experiment system or physical system, usually things happen at the finite temperature, even though they could be very small, but still finite temperature. And also, if you slightly go away from this from the critical point, there's some we want to compute the physical properties near this quantum critical point. So theoretically, the method can be for this problem is the conformal perturbation theory that the action of our system is given by the action at the critical point and also introduces perturbation. So to compute the conductivity near the quantum critical point at a small but finite temperature, so the conductivity is given by the two-point correlator of JJ at non-zero temperature and also for the coupling G slightly away from the critical point. So this two-point function, actually, if you use conformal perturbation theory, then actually this two-point function is determined by the OPE at the critical point. So in the JJ OPE, the leading order contribution is the unit operator or corresponding Vicam of the system, and also the leading relevant singlet Skinner. And the set contribution comes from stress tensor. So, for example, for this, there's a classical example for this critical point. It's given by the O2 Wake model, and it describes the insunator and the superfluid quantum phase transition. And if we apply JJOP and also use the conformal perturbation theory, people find that the conductivity near this quantum critical point is given by this formula. So for this parameter, the Cg and the Ct, they are the single charges of the O2 Wake model. Delta S is the skin dimension of the singlet Skinner. And now we know these parameters from the larger expansion. And also in this expression, it's very important to know lambda JJS and also lambda JJT, the current super correlators. So So our goal is to compute this kind of super correlator so that we can understand the conductivity near the quantum critical point. So firstly, let's go back to the position space, because as we know that because of conformal symmetry, we can almost fix the kind of super correlators in position space. It's given by this formula. And its Fourier transformation gives the super correlator in momentum space, but there could be some difference from contribution from the contact terms. So this is in general, even if you take Fourier transformation, as I mentioned before, you are given one loop integral, and in general, the integral is very complicated. And then if you take a series expansion on the leading or subgraph, there you will get a leading term, which you can get two pieces, one from two different subgraphs. So there's one piece comes from the subgraph, which only depends on the momentum p, not q. So it's given by this one. So our strategy to compute the sublinear corrections for the single charge lambda JJS is that firstly we take a subgraph expansion of the Feynman diagrams, and then we find the subgraph sector which match this singularity. This part is just fixed by the conformal symmetry. So we want to reproduce this term from Feynman loop computations and also extract the sublinear correction to the coefficient lambda JJS. So in the Owen-Vector model, actually, we have two different relevant skiners in Owen-Vector model. One is the Owen-Tristan symmetric skin. Another one is the critical boson, the Owen-singlet skinner. Because both of them are skinner. So therefore, safety constraints applies to, this formula applies to both the SIG and also S. Which one? Sorry, say it again. 5-4? Oh, you mean higher rank representations, right? Oh yeah, thanks for the point. But for that skinner, it won't appear in the JJOP in the second sector. Yeah. Yeah, but in principle, yes, people can also compute the JJ for the rank 4 tensor skinner. So this for this lambda SJJIJ, it could be important for the bootstrap studies. But it won't play role in the to compute the conductivity. But here I want to show the sublinear correction to this OP coefficient as well, because there will be some interesting property appears. So for this JJSIJ, that's the Owen-Tristan symmetric skinner. So and also JJS, they respectively correspond to the two different set of subgraphs. So let's consider the Feynman diagrams for the JJSIJ. So they're given by these two loop or three point Feynman diagrams. So again, we use the set of subgraphs. So for the JJSIJ, we can separate the loop integrals into two pieces, two different set of subgraphs. So this is I uppercase gamma, and this is I lowercase gamma. As I mentioned before, they correspond to different singularities of the external momentum. So from this computation, it's straightforward to use the method subgraph to compute all these Feynman diagrams, and then finally it leads to the this is the leading order OP coefficient, and this is subleading order OP coefficient. So the interesting point comes from the JJ singlet skinner. So here it's much more complicated because this is singlet, so we can draw three loop diagrams for the subleading order correction. And it makes the method of subgraph more necessary to do the computation. And again, similarly, we can use the method of subgraph. Now, because for the JJS singlet, we have in the Feynman diagram, we have extra propagator from the critical boson. So this one, it has propagator 1 over q squared 1/2 d minus 2. So that means compared with the previous JJ SIJ Feynman diagrams, here we have one more propagator from the critical boson. And because of this critical boson, it switches the singularities of the two subgraphs. So now for this subgraph, it has a singularity. Its singularity in P is in Q is cancelled, removed by this propagator. And and similarly for the three loop integrals, we have this subgraphic expansion by these three subgraphs. So again, they correspond to the subgraph with singularities, without singularities in Q. So therefore they consist with this sector, and they can just for this subgraph they can introduce or contribute terms that match the position space result. So this is a after we combine all the ingredients together, we get the result for the 3-point coefficient of this in 3D. We just get the result in 3D. In general dimensions, the computation is too complicated. And the larger result is by this one. And here, actually, in 2019, there's a team, Bootstrap group in Pisa. They get the result of a lambda GDS near 0.645. So if you compare the two results, we can see that the larger result is quantitatively close, but there's a notable difference. But that's not weird because for equality 2, we expect there will be some difference between the error bar will be notable. But still, it means it shows that this for the kind of super-correlated larger expansion to the sublinear order can give us some helpful information about this physical meaning of the 3-point coefficient. Okay, let me summarize the result here. First, the background is that the motivation is that the current 3-point correlators, they have a very broad application in condensed matter physics and also conserved bootstrap and some other directions. And the main result of this talk is that we developed a systematic approach based on subgraph expansions to simplify the Feynman loop integrals. And because of the conformal symmetry, the interesting point is that the high loop multiple point Feynman diagram information can be decoded from the lower loop Fourier point subgraphs. And this result could be applied. The sublinear correction for the current 3-point correlators could be applied in a bunch of directions. And another interesting question is that the conformal, it seems that from the lesson we learned from the 3-point computation is that the conformal symmetry and also the Feynman diagrams, it seems that there are some interesting connections that can help us to decode the high loop information from the lower loop subgraphs. So the question is, can we do the similar things for the 4-point correlator and also find some interesting connections between the analytical bootstrap and also the Feynman diagrams? That's all. Thanks.
Any question?
Basically, not identify which tensor structure that will be calculated in the diagram. It's like the efficient, and the rest is fixed with the problem. But
yes, that's right.
are you finding that in addition to that, you do this subgraph expansion? Do I understand correctly?
Here, actually, yeah, I feel it's kind of not that difficult to fix the extra terms. So I just put them together.
Because at the end, it says, say, if you start putting all of the diagrams together, very complicated expression.
Yes.
It has to simplify the solution, the general solution that we have. So you only need to identify three numbers. This complicated expression.
Yeah.
And then in the paper, it said again, you want to identify that number, the tensor structure, let's say, contains E1.
Yeah.
That coefficient of that, you don't need to compute anything else.
You're right. That's true. So, for example, on Klablov, JMB, they computed the current 2-point correlators in 2016. In their paper, they just focus on the leading term. They just threw all the data terms away. So, yes, you're right. You're right. And also here, we can also do that. Yes, but in my computer, just technically, you don't need to. As you said, you just need to trace a few parts of the tensor structure. Then for all the other parts, you can fix them by conformal symmetry. That's true. It's true here as well. But in my computation, technically, I just keep all the terms because when you compute the Feynman diagram, it's easy to make some mistakes. So those remaining terms can help me to do some cross check. Yeah. But you're right. So in principle, you just need to pick up a few terms, and then all the other terms can be fixed by conformal symmetry. Yeah. Yeah. Sorry, I didn't mention too much about the. So there's another method that you can just directly go to momentum space and solve the conformal order identity and some other equations just in momentum space, and you can get the answer directly. You don't have to really solve it. Yeah, that's another way, but I didn't go that direction because I need to compute the Feynman loop diagram, so it's a little different. Yeah, but I believe that if you introduce that method, it can help to simplify some of the computations. Oh yeah, that's a good point. Yeah, thanks. That's my future plan. Actually, yeah, I think one of the long-term goal of this another direction is that I want to compute the sublinear corrections or current super collisions in some mathematical field theory. And here, so again, here I just mentioned just party even second, but I think it's possible to directly generalize to introduce the party or the sector, and then so we need to do two things. One thing is that in the saved super collator side, we need to know more information of the current super collator in momentum space with all the sectors. And then for the Feynman diagram sector, I guess I didn't do the computation yet, but I believe it should be doable. I think yeah, that's an interesting point. For example, there are some interesting questions that I believe U1 QD3 with some mathematical companies. There are some interesting applications in conserved physics. And also another interesting point is that there's some mathematical theory in the large limit or in T-Hoff limit. So I want to try if we can compute or verify the 3D bosonization duality at the subleading order 10. Yeah, you and Madison just compute the leading order kind of supercollators, right? So it'll be interesting to know if we can verify this at the subleading order 10. Yeah, but that'll be much more difficult than this one. But that's another motivation for me to develop this method to do the computation.
So maybe one more question slash comment. So when you did the OP, when you're looking for speed, so
If you change OP, right?
expand quite often I'm watching
Let me go to that piece.
the low momentum expansion or high momentum.
Oh, this is a high momentum expansion.
Yeah, so for instance, yeah, so when you look here, if you look at the frequent function JJS,
Yes.
okay, that gives S in dimensional plane. Only becomes much of
The more, you mean, yeah, because here you need to know the vacuum expectation value of S. So is that the point? Yeah.
expansion.
Oh, okay. Okay. I didn't know that. Oh.
Take the account or did just match? I think what you said is would match it. Just look at the right similarity.
Yeah, here I just computed the OPE lambda JJS in the safety side. Uh-huh. Uh-huh. Oh, sorry. Sorry. Let me clarify. You are talking about the for the superconductor JJS, and in the momentum space. And if you take the small p or high p, large p expansion, and your point is that there are going to be some other terms beyond the OB terms. I guess I'm not quite sure. Yeah, they correspond to the two pieces here. Here we have two pieces, right, in the subgraph expansion. And let me go to the here. So indeed, actually, it's possible that we have two pieces. So which one is more dominating, it's not guaranteed. But for me, and I know they have different signal behavior, right? So I can separate these two terms safely. But if you want to compare which one is more dominating, indeed it depends on. Mm-hmm. But for Skinner, here is a Skinner case. Well, yeah, I don't know if your point means that here for these two different subsectors, they could be depends on the skin dimension of beta S. The two different sectors could have different needing contribution, right? Is that the point?
Yeah, the question is whether it's not.
Okay, that's a good point. I think I agree that problem is we need to think about carefully. But actually, I think that problem can be solved by the fact that we have for the two different contributions. It's true that one of the contributions could be more dominating in different region for different parameter space of the data S. But because the two different sectors, they have different signal behavior. Therefore, we can always trace them correctly. Yeah. Even though, for example, the another term is more dominating, that's possible, but it has different signal behavior. Okay, yeah, thanks. Anyway, thanks.
Any other question? No? Let's thank the speaker again.
Thanks.